All right, I'm back. This is video number 2. I'm actually filming this on the Friday of homecoming week during my short planning period. So if somebody pops in screaming some warrior pride stuff, then you'll know that's why. So here's a recap. This video has to be under 15 minutes, again, for my software. So the first video, we talked about how you can find the derivative using shortcuts. And a review of the shortcuts, which is if you ever take the derivative of just a number, then the derivative is always 0. If you take the derivative of, say, a linear function like a 2x, then the derivative of that is just going to be 2, the constant in front. Okay? If you take the derivative of something that has an exponent like 2x to the third, then the shortcut rule is you bring the exponent down front, so the 3 goes down front and joins the 2, and that makes 6. And then you subtract the exponent by 1, so 6x squared is the derivative. And the last rule was a combination of what if you have like x squared plus 6x, something like that. How do you find the derivative of that? Well, you just take the derivative of each individual piece. So the derivative of x squared would be 2x, and the derivative of 6x would be 6. So those were our derivative shortcut rules. But what you found out towards the end of the video when you looked at the examples is that a lot of the functions that we deal with aren't in the proper form for us just to go straight to the rules. So I want to refresh your memory on the 3 most primary types of problems in which you will have to do what we called the rewrite phase. Okay? Here are some times when you have to rewrite. We do not have a rule to take a derivative of a square root graph. Look to the left. I don't see a rule that mentions a square root graph. But what we can do is we can rewrite this as y equals x to the 1/2 power. Now we do have a rule where you can take the derivative of that. And the derivative would be bring the exponent down front, subtract it by 1, 1/2 minus 1. And then we have to kind of clean up our final answer. And since it's a negative 1/2, that's going to take it down to the bottom. And since this is a 1/2 on the front, it stays as a 1/2. So that's the first thing we have to rewrite, our square roots. Okay. The second thing that we have to rewrite is if you have an x on the bottom. So let's say we're trying to find the derivative of 1/x squared. There's not a rule for an x on the bottom. So all it takes is a simple rewrite and change this 1/x squared to x to the negative 2 power. Now we can say bring the exponent down front, subtract by 1. There's our derivative. That should say y prime. That's our derivative. But we need to clean that up a little bit. So the negative 2 will stay up top. But this x to the negative third, we need to write it in the denominator. Okay? And then the one final thing that we need to do is sometimes you might have a quantity. So you might have a function that's like 2x plus 2 squared. And they tell you to find the derivative. Well, we haven't done a rule yet where we can find this derivative. So what we need to do at this stage in the game is just actually do 2x plus 2 times 2x plus 2, which will be 4x squared plus 8x plus 4. Now we are ready, after a quick little simplification, we're ready to then find the derivative of this, which would be 8x plus 8. And then the derivative of 4 is 0, so you don't need to write the 0. Okay? So when you practice some of these practice problems today, all you did yesterday in class was watch the videos, and hopefully you kind of watched them a couple times and paused and maybe talked to one another. If not, when you start working on problems in a little bit, talk together. Work through these, especially since I'm not there. Use one another, and I'm ready for questions when I get back on Thursday. But there are 2 other concepts that we need to hit. We're 4 minutes into this video. I think each of these concepts will take about 3 minutes apiece, and so this video will be shorter than the last one. And what I want to talk about is reminding you what a derivative does and what a derivative is. Let's use a very basic graph. Y equals x squared. Okay? I choose that because we know exactly what it looks like. It's a parabola. Okay? Let's put this, we'll put a tick mark here, tick mark here. I'm just estimating. I know this isn't great. Okay? So that's the function. So then what would the derivative help us do? The derivative is also a function. The derivative of this would be 2x. And what I like to call the derivative sometimes is I like to call it the slope calculator. When we plug in things into the derivative, it will give us slopes. Okay? So what I mean is, if we took, oh, my eraser's still busted, so that line's going to stay there. If we took y equals x squared, which is a regular function, and we made an xy chart, we're plugging in x values. 0 spits out a 0, 1 spits out a 1, 2 spits out a 4, and they're giving us actual y coordinates. But if we do the same type thing over here with our derivative, it doesn't give you y coordinates. What it does is if you plug a 0 into the derivative, it's going to tell you the slope at that particular point. If we plug a 1, it's telling me the slope is going to be 2. If we plug in a 2, it's telling me the slope is going to be 4. And let's see if that actually makes sense. If we go to the point 0, 0, I'm putting a red dot right there. Does the slope at that point, if we were to draw a tangent line, does it make sense that the slope is 0? Sure. What about if we go to the point where x is 1? So x is 1 right there. Does that line look like it's a slope of 2? Sure. Looks like up 2 over 1, up 2 over 1. What about if we go to when x is 2, that point? Does that slope look steeper, more like 4? It sure does. So I want you to take this concept away. This is crucial. The derivative that I'm circling here in red, it finds instantaneous slopes. It can find you slopes at particular points, slopes of tangent lines. Okay, all those red lines that I drew, they're only touching my quadratic in one spot. Those are slopes of tangent lines. Okay, instantaneous speeds, instantaneous rates of change. So you might have a problem. Why did I just teach you that? You might have a problem that gives you a function that says y equals 4 over x squared, and we want to know the slope at the point 2, 2. What's going to be the slope at that point? Well, what do we need to find the slope? We need the derivative first. So I'm going to actually rewrite this to be 4 times x to the negative 2. Here's where the rewrite stage comes in. And then I'm going to go find my derivative. I'm going to find my slope calculator. And how do you do that? Well, you go back to your shortcut rules. We bring the power down front. That makes negative 8. We subtract it by 1, so that's negative third. So our actual derivative is going to be negative 8 divided by x cubed. This is my derivative. And then the question asked me, I want to know the slope at this point that I just circled in red. We want to know the slope at that point. The point is 2, 2. They're going ahead and telling us that. But they want to know the slope at that point. So if I take this x value and I plug it in, it should give me the slope at that particular x value. So what is negative 8 over 2 cubed? That's negative 8 over 8. The slope should be negative 1. And just so you can visualize what a 4 over x squared graph looks like, a 4 over an x squared graph will look like this. Let's see if the slope is negative 1 at that point. Just doing some trig today, pre-cal. So we've got 4 over x squared. Let's see if at the point when x is 2, let me go zoom 6, stop, zoom 6. Let's see if at 2 the slope looks like it's negative 1. If you imagine a line being drawn right there, I actually think we can draw a tangent line. I forgot. Let's see if we can draw a tangent line. Oh, this is advanced stuff you guys are watching. This is like you're seeing like a clip from the movie before it hits the theaters right now. Let's go when x is 2. So look, I'm going to click and drag until it gets 2. Let's draw a tangent line right there. Yeah, buddy. That looks like a slope of negative 1 if I've ever seen one. It even gives us the equation, y equals negative 1.04. And since I was winging this and I was just getting pretty close, then you better believe that's a slope of negative 1. That's a walk-off right there. Okay, so there's proof. What does the derivative do? It helps us find individual slopes. And we can find them at points if they ask us. That will come in handy on your homework shortly. Here's the last concept. an important concept is how do we find horizontal tangent lines? Okay, horizontal tangent lines are crucial because, take a look at this picture. If I graph this graph, there are only 2 points on that entire function where the tangent line will be perfectly flat. That is right here. Can you imagine why that slope would be flat? And that is right here. Those are also probably the 2 most important points on the graph. That's the max and the min. So finding horizontal tangent lines and finding them quickly is a speedy way to find the max and the min. We can use derivatives to find maximums and minimums of functions in a very efficient manner. So the book will ask you, hey, here's a function. Find me the horizontal tangent line. So let me just pick a random equation here. I'm making this up, so hopefully it works out. Y equals x cubed plus 6x squared minus 3x minus 2. No idea what that looks like, okay? And let's say they want me to find the horizontal tangent lines. Well, what is the derivative at a horizontal tangent line? What's the slope there? And what's the slope there? I'm hoping in your head you're saying 0. The slope is 0. So to find an HTL, all you have to do is set the derivative equal to 0 and solve for x. And that will give you the, in this case, 2 times where the slope is 0. So I'm just realizing now that this might not factor, but let's cross our fingers and see if God delivered for us here. If I take the derivative of this function, we'll have 3x squared. And then when I do this, it'll be plus, bring it down, 12x. I'm finding the derivative right now. Minus 3. And then that goes away. This is not going to factor. Bummer. There's no way that 3 and 3 can add to be 12. But you get the gist. Let's pretend like this was a... Pretend like this was an 8. Pretending, okay? So what we would do then is we would say, okay, 3x and x, 3 and 1. And so then once we set our derivative, which is that, equal to 0, what we're doing is we're finding the horizontal tangent lines. We're finding the 2 spots where the slope is 0. So we'd have one at 1/3. That would be one of our horizontal tangent positions. And we'd have one at -3 if I made this problem up with a little more thought than just winging it. Okay? So in conclusion, this is the last 20 seconds of the video, so listen up. You use your shortcuts to find derivatives, and that's the first thing you've got to master is how to use the shortcuts. But then we're going to start solving problems with them. We will find slopes at particular points, and we will also find the horizontal tangent lines at specific points. So I'll go ahead and put the assignment here. It's also online, but you're going to practice tomorrow. I mean, technically you can do it ahead of time, but tomorrow you're going to practice this. It's problems 1 through 21 odd, 27, 29, 31 through 37 all, and 39 through 43 and 47. That should take the entire class, okay? And remember, when you're looking at the textbook, if you see a problem in red, make sure you go to math, you go here, Calc View, and you click on our calculus book, and you can go down and go to chapter 2, section 2, exercise whatever, and you can watch a video of that particular problem. Are you kidding me? Okay, so use Calc View, use Calc Chat, use your neighbors, use your textbook, but just don't text me because your boy is laying on the beach enjoying my last day of freedom before basketball ramps up, all right? So good luck to you guys. Send me an Academy Central message if you have questions, but we will reconnect next time I come in. Have a great day.